Hey class, today we're going to be going over lecture 14, so chemical reactions. Um, this is usually a really cool lecture because we go talk about all these different chemical reactions and then we actually do like demos with them. Um, but unfortunately we are not in the classroom and doing demos, so it's going to be maybe not as exciting as it would have been, but hopefully it's okay. All right, so let's start it off with a quiz real quick. Okay, so this is a review from the last couple lectures. So what is the shape of aluminum chloride? Okay, so first off, we're going to draw the Lewis structure. So aluminum has 3 valence electrons because it's under boron. Okay, and connected to 3 different chlorides. All right. Okay, just like that. Cool. And what type of intermolecular forces will aluminum chloride experience? Okay, so we need to first talk about what kind of bonds we have here. So between aluminum and chloride, chloride's electronegativity is 3.0 and aluminum is 1.5. So that's a difference of 1.5. So it's actually going to be a polar covalent bond. Okay. And so we have polar bonds here. I didn't draw this great, right? Since aluminum has 3 electron clouds around it, it's actually going to be a trigonal planar shape, right? So if I drew the true shape, it would look like this. So you have these dipoles running out from the center, and they would all cancel out. So even though you have polar covalent bonds, you'd have a non-polar molecule. Okay. So the shape would be trigonal planar, so either D or E. And then if you have a non-polar molecule, then you're going to have dispersion forces. So you should get E here. Cool. Okay. Oh, sorry. Yeah, this is one of the demos that we do. It's called Elephant's Toothpaste. If you want to look it up on YouTube, there's a bunch of people that have done it. But basically, hydrogen peroxide. You have this H2O2 that breaks down into water and oxygen. So we're going to be talking about some different kinds of reactions and like different classes of reactions and how we classify them and stuff like that as we move through this lecture. So fundamentally, a chemical reaction, what's happening is bonds are breaking and then bonds are forming. Okay, so just kind of illustrate that with this hydrogen, with the demo that we would have just seen. Maybe you went and watched it. So you have hydrogen peroxide here on the left side, okay? Hydrogen bound to oxygen, and then down to another oxygen, down to hydrogen. So what happened is these red bonds are going to break when the chemical reaction occurs, okay? Those break apart. And so then you have the hydrogen, this oxygen, and then this oxygen hydrogen here still left. And the next part of the reaction is to reform new bonds. So this oxygen forms a new bond with that hydrogen here. And then these 2 oxygens form a bond between each other, okay? So you're left with water and oxygen. And chemical reactions, kind of the driving force, like you might ask, like, why does this even change? Why doesn't it just stay how it is? And a lot of times molecules will stay how they are. Later on, we'll be talking about like activation energy. So you have a molecule like hydrogen peroxide here that's going along, and it's kind of unstable, okay? But it's not going to do anything unless it's provoked, basically. So if it receives a certain amount of energy, that energy allows the bonds to break. So you just need to add enough energy to break these bonds. And then it says basically what's going on at that point. It says, well, I could go back to hydrogen peroxide, right? That's a possibility. But since I've broken these bonds, what's actually better is to go down to water and oxygen. Those are more stable molecules than hydrogen peroxide. So if you add a little energy to break the bonds, at that point, you're just going to go to whatever is most stable, which would be the water and oxygen. Okay. Anyway, don't worry too much about what I just talked about there. Just talking about why this actually happens. Yeah, so the atoms are rearranged to form one or more different substances. The other thing to notice here is that we always preserve the elements on each side. So if you start with 4 hydrogen atoms, you need to end with 4 hydrogen atoms. If you start with 4 oxygen atoms, you need to end with 4 oxygen atoms. So this gets us into balancing chemical equations. So sometimes a chemical equation as written will not be balanced. So you might have more hydrogens on the left side than on the right side or something like that. So we're going to talk about how to balance these to make them more accurate. So in a balanced chemical equation, you want to make sure atoms are not lost or gained. So the number of atoms in the reactants needs to equal the number of atoms in the products, just like we saw on the previous slide. Here's an example. So if you mix hydrogen and oxygen, you can get water, okay? We have 2 hydrogens on the left side here and 2 oxygens on the left side. And on the right side, we have 2 hydrogens, but we only have 1 oxygen. So we need to balance this. So what we do is add coefficients in front of the different compounds in order to balance it. We can add whole number coefficients in order to do that. So, well, before I get there, maybe I'll walk you through the process of what I would do here. Okay, so I know I have 2 hydrogens over on the left and 2 oxygens, and then on the right I have 2 hydrogens and 1 oxygen. So I need to multiply this whole water molecule by 2 because I need to have 2 oxygens, right? So now I have 2 oxygens on the right side and I have 2 oxygens on the left side. But when I multiply this by 2, I actually multiplied this H2 by 2 as well. And so I have, now I have 4 hydrogens on the right side, right? Because each water molecule contains 2 hydrogens and I have 2 water molecules. So 4 hydrogens on the right side. So that means I need to have 4 hydrogens on the left side. So if I add another 2 here, I have 4 hydrogens on the left, 4 hydrogens on the right, 2 oxygens on the left, 2 oxygens on the right. And then it would be a balanced chemical equation. Okay. Awesome. All right, go ahead and try this. So if you want to try it on your own, go ahead and pause it. If you feel like you haven't got enough exposure, then just keep watching and we'll go through it. Okay, so if we take a look at this, we're going to have, I might draw a little table here. So on the left side, we look at number of carbons, hydrogens, and oxygens. Then on the right side, carbons, hydrogens, and oxygens. Okay, so right now we have 1 carbon, 4 hydrogens, and 2 oxygens. And then on the right side, we have 1 carbon, 2 hydrogens, and 3 oxygens. Yeah, okay. So as a general rule, I wait to add coefficients to single elements, right? So like if it's just O2, just oxygen, I'll wait for a while to do that one. Because if I add a coefficient to like water or CO2, it's going to affect 2 different elements. If I add it to just the oxygen, it only affects 1 element. So it's easier to leave those ones till the end. Okay, so I have 1 carbon on each side, so I'm good. 4 hydrogens on the left and 2 hydrogens on the right. So I need to add a 2 in front of this water. Okay, so then I'll just take it kind of stepwise here. Show this. Okay, so if I do that, I still have 1 for 2 on the left side, but now I have 1 for 4 on the right side, right? So I have two oxygens here, two here, that's 4 oxygens. 1 carbon, 4 hydrogens. Yeah, okay. Okay, so now all that's left, I have the same number of carbons on each side, the same number of hydrogens on each side, but I don't have enough oxygens. So now I can just add a 2 here, and since that only affects oxygens, right, this is going to change it to 1, 4, 4, 1, 4, 4. So now we're balanced, okay? Okay, this is just a PowerPoint kind of walking you through it in a different way. Well, same thing, but written out so you can see it. Okay. All right, again, let's try another one here. Go ahead and try and balance this equation. All right, so let's walk through it. So we have, I'm gonna draw my little table again. Cobalt, hydrogen, and chlorine. Okay. Cobalt, hydrogen, and chlorine. All right, so here we have 1 cobalt on the left, 1 hydrogen, and 1 chlorine. And on the right, we have 1 cobalt, 2 hydrogens, and 3 chlorines. Okay. All right, let's go ahead and do this. So I know I need more hydrogens on the left side, and I need more chlorines on the left side. I need to do at least 3 chlorines, right? So if I put a 3, because I have 3 chlorines on the right side, so this number needs to be at least 3, I know that. So I'm going to do 1, now I have 1, 3, 3, 1, 2, 3, okay. So now I have too many, let's see, yeah, too many hydrogens on the left side. So in order to get, and this is a little, I don't know, a little trick I think that's helpful. Everything's good here except for the hydrogens. I need 1 more hydrogen here is all I need. Unfortunately, this is like an H2. So if I put a 2 in front of this, this would go to 4, and then I'd have to change this to 4, and then it'd be going back forever, right? It would take a long time to do it that way. But what I could say is actually, let's just multiply this H2 by 1.5, right? If you multiply, right now it's just a 1. If there's no coefficient, then it's a 1. 2 times 1.5 is 3. So as it sits here, I have 1, 3, 3, 1, 3, 3. So I'm balanced with what I have here. I have a 1 here. That's, you don't write it if it's a 1. 1, 3, 1.5, 1. You can't leave decimals or fractions in coefficients for balanced chemical equations. But in order to get rid of it, you just double everything, right? So I could actually, at this point, just say I have 2 cobalts, 6 hydrochloric acids, so 6 HCl's, 3 hydrogen gases, and 2 cobalt chlorides. Okay. Again, there would be a way to do this without going through that 1.5, but sometimes if it gets you balanced, it's easier to just do like a 1.5 or a 2.5 or something, and then get rid of that 0.5 by just doubling all the coefficients. Okay, so that's what I did here. Okay, let me get rid of my writing and we can see what the PowerPoint has for us. Okay, so this doubled the HCl's. And then, let's see, I'm trying to follow this. Okay, so then basically, at that point, after doubling the hydrochloric acids, there's 2 chlorides and 3 chlorides over here. So to get to the least common multiple, you multiply this one by 3 and that one by 2. And then you'd have 6 chlorides on the left, 6 chlorides on the right. And then at that point, you have 6 hydrogens, so you need to put a 3 in front of this, and 2 cobalts, so you need a 2 in front of it. So you get to the same answer we did. It's a different way to go. So it doesn't really matter how you get there, it just matters that you get there. So whichever one of these methods or ways looks best to you. There's probably other ways to do it too. So the nice thing about these problems, like on a test, is that it's hard to get wrong as long as you are persistent, especially with multiple choice. But if it's like a fill in the answer or something, the only way to really get this wrong is either to just mess up your math a little bit or give up, because you can always check your answer right at the end. Once you get to this point, if you think you have the right answer, just count up, right? I have 2 cobalts on the left, 2 on the right, 6 hydrogens on the left, 6 on the right, 6 chlorides on the left, 6 on the right, and then you know you got the answer right. If it doesn't work, then you got to try again. Okay. All right, speaking the language. So you have integer coefficients to balance. Okay, so those are the big numbers that go before each compound. You've also probably seen these little letters or symbols in parentheses. Those indicate the state. So for example, if we go back to this one, cobalt is a solid, hydrochloric acid is a gas, hydrogen is a gas, cobalt chloride is a solid. These are all like at standard temperature and pressure. Okay, so anyway, so basically, if you need to write out a chemical equation and include these, here are kind of the rules that should cover most everything. Not most everything, a lot of things. Okay, so diatomic gases. Okay, so anytime you have these like hydrogen, oxygen, nitrogen, fluoride, chloride, these are all diatomic molecules. So I think we've talked about before how like oxygen doesn't exist on its own. It's going to be paired with another oxygen in order to complete the octet, right? That's true for all these, except for hydrogen. And these all exist in the gas phase at standard temperature and pressure. Bromine is actually a liquid at standard temperature and pressure. Then iodine is a solid, and carbon on its own is a solid. So like carbon would take the form of a diamond, right? Diamonds are carbon, and lead, like pencil lead, is carbon as well, so graphite. Anyway, that's another cool thing you can talk about. Man-made or artificially made diamonds are just a bunch of carbon pressed really tightly with lots of heat and pressure toward a facility in Orem. It's called US Synthetic, and that's what they do. They basically take a block of like looser carbon, so like graphite or something like that, and then they compress it with heat and temperature into a diamond. It's really, they use it for diamond tips on like saw blades and stuff like that. Another kind of weird thing is like our body's made mostly of carbon, so some, I've heard companies that will like take the remains of somebody if they're like cremated and take the carbon and compress it into a diamond, and then people can wear it on jewelry. So I don't know, I wouldn't do it, but you know, everyone's got their own opinions, so that's all good. All right, moving on. So metals and metalloids. All right, so those are going to be solids almost always. Mercury is the exception. That's like the liquid metal. I don't know if you've ever seen mercury. It's in like thermometers and stuff like that. Well, it used to be. They don't really use it anymore too much in thermometers. And then compounds. So if you have salts, they're generally solids, like table salt, right? It's a solid. The exception here is if you dissolve the salt in water. And the way you'd know this is the problem would say dissolved in water or something like that. If it doesn't say anything, you might just assume if it's a salt, it's going to be a solid. Okay, but if it's dissolved in water, you would put aqueous. Okay, so yeah, so kind of look for those hints. If it points out that it's dissolved in water or that there's water in the reaction or something, you would write aqueous. Otherwise, put salt or solid. And then covalent compounds, those are really hard to tell at first. So don't worry too much about those. It should be clear in the problem or something like that. I'm not going to expect you to know that ethane, right? So like if you had C2H6, I'm not going to expect you to know that that's a gas, okay? Because if you had something heavier, like maybe you have C12H26, something like that, that would probably be a solid. So yeah, hard to tell with covalent compounds. It takes a little practice, but don't worry about those too much. But the rest you should know. I would expect you to know the rest. Okay. All right. Types of reactions. So we're going to go over some different, all these different types of reactions here. And this is where it would have been cool to be in class and show you an example of all these reactions, but that's okay. We're going to go over the basic ideas here. So combination reaction, pretty self-explanatory. A plus B gives you an AB compound where these two are bound together, okay? Okay, an example would be, see, this is probably a better example. Don't worry about that one too much. So yeah, magnesium plus oxygen gives you magnesium oxide. So this isn't gonna, it doesn't combine perfectly. This one's hard to see. But again, this does they do combine to form, this is carbonic acid. But here it's a little easier to see. So you have magnesium plus oxygen gives you magnesium oxide. And even though you have oxygen like O2 in this form, right, doesn't necessarily mean that you're going to have MgO2. That would just depend on whatever metal you combined it with. But really here you're just looking for one element plus another gives you this compound. Or in this case, one compound plus another gives you a compound that's mixed of both of them, basically. They're easy to identify because usually you just have two reactants and then you have one product, okay? And that's really what you're looking for. Two reactants, one product, okay? All right. Lots of examples there. Okay. The opposite is where you have one reactant and two products, okay? So that's a decomposition reaction. So this could be like water splitting into its hydrogen and oxygen separate components. Okay, so applying electricity to water, you might be able to pull out some hydrogen gas and oxygen gas. TNT, this is trinitrotoluene. It's going to decompose into 4 different products. So decomposition would be 2 or more products. And same with combination, 2 or more reactants going into a single product. One reactant going into 2 or more products would be the opposite there, okay? And then for the single replacement reaction, you basically, A joins up with BC and then knocks off one of these two, right? In this example, A joins here and knocks off B, and so you get AC plus B. So these ones are a little, hopefully you can see them pretty easy. They start with 2 and end with 2 products, so that's one way to notice it. And then you have, you'll have one of your reactants will be a single element, and then one's a combination. So the zinc combines with the chloride here, and then kicks off the hydrogen. So you get zinc chloride and hydrogen. Same here, you have iron that combines with the sulfate, and the copper comes off. Okay, so those are single replacement reactions. And then double replacement, okay, it's where you start with a compound, or 2 compounds, and you end with 2 compounds, but you basically switch places. So for example, this, the cation here, okay, so you notice there, if you, these are all like ionic compounds, I think for our examples. So you have this cation that combines with the anion, this iodide, right? And then the sodium would combine with the nitrate here. So you get this compound and that compound, okay? So you can see how they combine. They switch places, basically. Another example, you have your zinc that will switch places with, oops, I drew it too far. Zinc switches with chloride, right? And hydrogen, or no, zinc joins up with chloride, and then the hydrogen joins up with the sulfur. So you can see how they kind of go. So you get zinc chloride and hydrogen sulfide. So cool. All right, predict the products of each reaction. So we learned 4 different reactions just now. So go ahead and pause it and try and predict what you would get out of these. Okay, cool. So let's walk through these. So with the combination reaction, obviously these two are going to come together, okay? And your potassium joins up with the hydrogen. You get potassium hydride. We haven't really seen hydrides too much, but anyway. And then if you balance the equation, you would get this. Decomposition, so you have mercury, right, and oxygen. So it should split up into mercury and oxygen. And you remember that oxygen's always in the O2 form, right? You're not just going to put an O by itself. And then mercury is the one metal that's a liquid. And then oxygen, diatomic oxygen is a gas. And then you can balance the equation from there. So single replacement, you notice, I think the easiest way to look at these is like your potassium, right? This is a positively charged ion when it's on its own. The iodine is a negatively charged ion when it's on its own. And the chloride is a negatively charged ion when it's on its own. So that means that the negatively charged ones are going to switch, right? So you'd get, well, it's potassium chloride, so, and iodide. And the reason the negative ones switch is because if you switch potassium with chloride, you'd get 2 negatively charged ions together, which isn't going to happen, right? So you need to switch the negatively charged iodide with the negatively charged chloride ions. Okay. And then double replacement. And you have your positive and negatives here. These are ionic compounds. And so this positive copper is going to combine with the negative sulfide, and the positive sodium is going to combine with the negative chloride to get copper sulfide and sodium chloride, and then balanced. And here we have aqueous. Again, this would, when you're drawing out a reaction of salts, generally you'll see aqueous, just because they can't really react in their solid form, right? You can't just like mix 2 salt powders together. They're not really going to do anything. The way to get them to react is to put them in water. And so if you're drawing out a reaction with salts, generally you'll put aqueous more often. Okay. Hopefully the homework problems help you kind of notice more about when it's aqueous and when it's solid there for the salts. I think most commonly though, you're going to see aqueous. Okay, so then we have oxidation reduction reactions. So this first bullet point here just kind of tells you that decomposition, addition, any of these reactions we just talked about, they can be oxidation reduction reactions. So it's kind of its own little class. And basically an oxidation reduction reaction, sometimes you'll hear people say like redox, they just put the two together, reduction, oxidation. Anything that involves the transfer of electrons is a redox reaction, okay? Typically release a lot of energy. And here's some examples of where you might see redox reactions, okay? All right, so one of the most common ones and ones that we're probably familiar with is the rusting, okay? So nails and certain tools and stuff like that, a lot of stuff is made out of iron. So iron can gain oxygens and it becomes iron oxide. And this is the rust that you see, right? This is rust color. This is rust right here. Okay. So we need to identify, in order to see where the electrons were transferred, know where the electrons started and where they went. So in iron oxide, if we cut this up, right, like we did when we were naming ionic compounds, iron would have a 3+ charge. Oxygen has a 2- charge always, right? So if we looked at where the electrons started, anytime you have a single element on its own, we generally just say it's, well, it is neutral, okay? So the charge would be 0. And then for oxygen, since it's on its own, oh, sorry, I'm tired. Oxygen, since it's on its own, is going to be neutral as well. So then we use these things called half reactions to help us see what's happening. So iron starts as iron 0, right, on the left side of the equation, and it goes to iron 3 plus. In order to go to iron 3 plus, it needed to give up 3 electrons, right? Oxygen goes from O0 basically, so neutral oxygen, and it ends up as O2 minus. And you have 2 oxygen over here, and each one goes to a 2 minus, right? So in order to do that, 4 electrons needed to be added, 2 electrons per oxygen atom to get you to this point. So then you end up with 2 oxygen atoms with a 2 minus charge, okay? So you can see that electrons were, they left the iron, right? Iron gave up electrons, and then oxygen took electrons. Okay, so if it's fully balanced, so if we use the coefficients from up above, all right, we had 4 irons, and they went to, you have 2 iron oxides, which was really 4 iron ions, okay, and that gave up 12 electrons. Then you had 3 oxygen atoms that gained the 12 electrons that iron gave up to go to 6 separate oxygen atoms. So here you have O3 times 2 is 6 oxygen, which you see here. Okay, and that gave you your full equation. What you just need to notice here is which element, kind of the big thing you'll have to answer is it an oxidation reduction reaction? And which element was oxidized and which was reduced? Okay, so we'll talk about that here, I think. Okay, so oxidation reactions, transferring electrons, okay? So what's oxidized and what's reduced, right? Oxidation is a loss of electrons. So if the element is losing electrons, it was oxidized, okay? Reduction is gaining. So people often remember this, they just say oil rig, okay? So oil oxidation is losing, and then reduction is gaining. So oxygen gained electrons, so it was reduced, okay? You can also do Leo-Ger. Loss of electrons is oxidation, gain of electrons is reduction. Anyway, whatever you find easiest. Okay. So, oh wait, we probably should point out something here. Oh yeah, I think I talked about this. So we would say that iron is oxidized, and we'd say that oxygen is reduced. Okay, so if the problem says which element was oxidized, it's going to be the one that lost electrons. And which one is reduced is the one that gained electrons. Okay, and so this is really helpful for ionic equations. The more helpful way to think about reactions with covalent compounds is going to be either loss of hydrogen or gaining of oxygen. So this will be more helpful in like Chem 285 when you're talking about pretty much all covalent compounds at that point. Okay, mostly organic chemistry there. So reduction would be, for biological systems, reduction would be the gaining of hydrogen or loss of oxygen. I think the easiest way to remember this is oxidation is gaining oxygen, right? If you just remember that, oxidation is gaining oxygen, which is really where the name comes from anyway, then you can kind of figure out the rest of it. The hydrogen is just always going to be the opposite. So if oxidation is gaining of oxygen, then that means it's also the loss of hydrogen. And then the opposite is true for reduction. So you could just remember that. But anyway, so if you look at this, let's say you have 2 hydrogens on this biological molecule, and you have this coenzyme. The hydrogens move over to the coenzyme. So because this molecule here lost hydrogens, it's going to be oxidized, okay? So this is the oxidized and this is the reduced coenzyme molecules that gain hydrogen are reduced. Okay, so if you're looking at biological or organic compounds, this would be, sorry, I shouldn't say organic, covalent compounds. No, organic, sorry, thinking it through my head. Organic compounds, which mean they contain carbon, or biological systems, these are generally the rules you'll want to use. If you dive in deep, you'll see that the rules are really the same as the ones from the ionic, but this is a bit easier to look at it this way. All right, go ahead and try this quiz real quick. Pause the video. Okay. So we have this combustion reaction. And combustion, you think of as like explosion, right? And that's what it is. You take a hydrocarbon and you combine it with oxygen and a little bit of energy, like a spark or something, and it's going to blow up and it's going to release carbon dioxide and water. It won't necessarily blow up, I guess. It could just light on fire. So like a lighter or something like that. So if we looked at which one is oxidized and which is reduced, so the carbon here is present on the right, and what happened to carbon? Carbon gained oxygen, right? And it lost hydrogens. So if it gains oxygen, that's oxidation. And then just the other one's going to be reduction, but reduction also is gaining hydrogens, right? So this oxygen gained hydrogen, so it was reduced. So it says which compound was reduced, so that would be the O2, right? Okay. All right, and then the last little quiz for today. Identify the reactant that is oxidized and the reactant that is reduced. So the best way to do these problems is I like to look at kind of the charge, or you'll sometimes see it referred to as like the oxidation state. So if we look at chlorine, okay, chlorine starts at a 0. It's neutral because it's on its own, just chlorine here. And then potassium has a +1 charge on it, and iodine has a -1. This is if we split it into ions, right? Because these are ionic compounds. If we look on the right, the potassium here has a +1 charge, the chloride has a negative charge, and then the iodine, since it's by itself, would have a 0. So chloride goes from 0 to -1. So in order to go from 0 to -1, it needs to gain electrons. Right? Then iodine that goes from -1 to 0. So in order to go from -1 to 0, it needs to lose an electron. So the gaining of electrons, right? Oil rig, oxidation is, oh sorry, rig. Reduction is gaining, right? So the chloride, this is the one that's reduced. Reduced. Sorry. Okay. Reduced. And oxidation is losing electrons, right? So the iodine goes from a -1 to 0. So you could say that the potassium iodide, basically the other one, is going to be the oxidized one. Okay, and that's how you'd figure out those ones. So, all right, hopefully that was helpful. And go ahead and practice all that in the homework, and we will catch you next time.